Okay, geometric sequences. What is the defining characteristic? Who remembers? Yeah.
My book's missing the pages. It goes from 217 through 219.
Okay, I'll have to deal with that afterwards. Yeah, the ratio, a common ratio, right? So what we have here, please listen, is we have R, which is the common ratio, right? And you can see what is happening is each time you're timesing by 2. So the difference is actually 3, but you're timesing by 2 to get from 3 to 6, and you're timesing by 2 to get from 6 to 12, and you're timesing by 2 to get from 12 to 24. Very important, the common ratio is the later term divided by the earlier term. So obviously a half and 2 are two extremely different numbers, and if you get it in the wrong order, you've got the wrong ratio, and it's going to make this very, very difficult, right? So this one, the second term is 6, the first term is 3, and the common ratio is 2, which makes sense. It's getting bigger and bigger and bigger, right? General formula for all geometric sequences is AR to the power n minus 1. In actual fact, there is an exception. Sometimes you can't see the common ratio in the very beginning sequence, but if you work out the difference, that one will always have a common ratio. So if you work out the difference between these things, and you say, well, that's a difference of 3, and that's a difference of 6, and that's a difference of 12, and that's a difference of 24, you see that you can always see it in the first difference. So if you can't see it in the actual sequence, you will always see it in the first difference, okay? But that's unusual. They usually give you ordinary ones. They give you ones like this one over here. A is what? Okay, it's A is, what did you say? Yeah, it's 3. It's the first term. So A is the first term. And so this is your sequence is going to be 3, and then times by 2 to the power n minus 1. If you have exponents that work together, so say your sequence turns out to be, for example, 4 times by 2 to the n minus 1, you would usually go and use the exponent rules and you would simplify it, right? So you would then make this into 2 squared, and you would add your exponents as usual, and you'd end up with 2 to the power n plus 1, right? So if you do end up with the same base, then please simplify your sequence. Obviously, in a situation like this, there's no possible way to simplify it. The one thing you definitely don't do is make it equal to 6 to the power n minus 1, because that's absolute rubbish, right? And then everything is going to be wrong. So that's basically what you did in year 11. You're going to use the same techniques, but now you're also going to do sum to infinity and sum of the sequence. Now, you should be able to see with a sequence like this one, you can't work out sum to infinity, can you? I mean, if you keep it, it's going to get bigger and bigger and bigger and bigger with every term. So if you wanted to go to infinity, it would be some sort of absolutely massive infinite number, right? Which is pretty much useless. So there are 2 different formulas for 2 different sequences. When your value of R is greater than 1, okay, then your sequence is never going to stop. And it's going to get bigger and bigger and bigger and bigger. And this is the formula for a sequence with a large R value. So very simple. You can see your first term is A, so going by our last little sequence where we had A was equal to 3. Just put a 3 inside there. Then this is 1 minus R. R was 2 to the power n. Now, that n is going to have to be the number of terms that you're interested in, because otherwise you are going to be doing that, as I said, forever, right? So let's find the sum of the first 6 terms. So then that's going to be a 6 over there, and that's going to be R to the 1 minus 2 to the power 6. And if you could just please check that you know the answer to that. Okay. So that's sum to infinity, at least just sum of 6 terms, right? Not sum to infinity, sorry. You can do sum to infinity, though. If you have R being a fraction, so say we have the sequence 6, 3, 3 over 2, 3 over 4, 3 over 8. And obviously, you only need 4 terms to tell what type of sequence it is, so I don't obviously need all of those, right? But you can see that what you're doing is you're obviously dividing by 2. So r is going to be equal to a half. Remember that you're going to work it out by saying the later term divided by the earlier term. And any later term divided by any earlier term is going to give you r. That's your simultaneous equation that you are going to use when they give you 2 terms and you want, or 3 terms, and you want to find out what r is or what a is, right? You're going to use division because that's what we're doing, okay? So this one, it's going to be Tn is equal to first term half to the power n minus 1. And you could rewrite that if you wanted to as 2 to the power minus 1. It's sort of silly. I wouldn't bother to do that. But you should understand that it's the same thing. So then this is 2 to the power 1 minus n, right? But you can leave it as a negative. You can leave it as a fraction. They won't mind, right? So you can leave the half as it is. It'll be fine. So for this one, there is a sum to infinity. Because those terms are getting smaller and smaller and smaller, you might remember from geometric distribution when we did that a few times, right? And those terms are getting tiny. So the next one is going to be 3 32ths and then 3 64ths. And it's going to get littler and littler and littler and littler and littler. So logically, they're going to get so tiny that by the time you add them up, they're not going to make any difference anymore. So you can work out the sum of the entire sequence because it tends to a certain number, right? So this is sum to infinity. Only applies when r is between 1 and negative 1. So if you have something big, then the sequence is going to be getting bigger and bigger and bigger and bigger and bigger, and obviously you can't work it out. It'll be some massive infinite number, right? But this one, because r is little, it's a fraction. Each time you're timesing by the fraction, so it gets smaller and smaller and smaller and smaller and smaller, and obviously eventually those numbers become so small they don't matter, right? So sum to infinity is a over 1 minus r. If I'm correct, both of these are given formulas. You don't need to know them. So a, of course, is, well, you do this one quickly. So obviously a is going to be equal to 6. You're going 1 minus r, which is a half, and obviously half fits into 6 12 times, as it always has. So that sequence is going to add up to 12. Okay, if you keep on adding and adding those teeny tiny fractions, the biggest possible number can end up to being is 12. There is a proof for that. And next year, you'll look at quite a lot of proofs for various things. But for this year, you don't need to worry too much. Can you please do... so there are the answers for page 274. You can see that A is 54 and R is 2/3. And you check that it really is a geometric sequence by comparing the two sets that you have. And very important, term 1 is A. Term 2 is AR, term 3 is AR squared, term 4 is AR to the power 3, etc., right? So here's page 275. They've given you the 5th term and the 2nd term. The important thing here is to write them in this format. And then you know that... well, the obvious way to get rid of a is to divide, right? You're multiplying, and when we multiply, to solve, we divide. So we're not going to subtract like we did with the arithmetic sequences. This time we are going to divide. So you can just put the bigger term over the smaller term, or the other way around, makes no difference. And then the two a's will cancel, and you will have r. Then you need to make r in terms of the same exponent. So if r cubed is 1/8, then you're going to have to think of something cubed. So it's going to have to be 1/2. Once you've got that, you've got r, which is a half. You've got the first term by substituting back into one of our two equations. So 9 is equal to AR. Substitute back in. A is 18. And there's the sequence. Once you've got the sequence, then the sum to infinity should be really easy. Just plonk those things in. There's your sum to infinity. The general term. If they give you the nth term, that's the general term. It's all the same thing. And we have got that over there. And notice that the general term is not n minus 1, so things are different here. You have to be a little bit careful. Okay. So because that is an n and not an n minus 1, You're going to have to work it out. First term is not 9. First term is minus 6. How will you find the common ratio? Just find the second term, absolutely. So you're just going to plonk the thing in, find the second term, which turns out to be 4. Common ratio, please remember later term over earlier term, right? Don't get it the wrong way around, because things will go badly if you do. And that's it for that one. They can present to you the sequence in one of two ways. So either they can say something plus something plus something, in which case they're giving you the sum of the sequence, but it's still the sequence, and the first three terms are still going to be y, or x, y, and x squared. And obviously, if you've got bunches of letters, you're going to be making simultaneous equations. So you make an equation based on the fact that every single arithmetic sequence, the common difference is the same between the second term and the first term, and between the third term and the second term. For geometric sequence, the defining characteristic is third term divided by second term is the same as second term divided by first term. So you make your two simultaneous equations. So here is equation 1. This is equation 2. I've then multiplied it by 2 because it's going to be much easier to push the two of them together if they both solve for 2y. So if 2y is equal to 2y, then x squared plus x is equal to 2x cubed. And so here they are combined, right? There's your combined simultaneous equation. Make it into the format that you are used to solving, right? If they give you a cubic, the chances that you'll be able to solve it easily are very, very good. They know you don't have a technique for doing this yet, right? So don't get a fright. Take out the 0, and now you've got a quadratic. Don't drop the 0. It is a solution, which I don't know if I dropped it over here. I did. Shame on me. I'm going to just put it back. So there it is. And there is our third solution. Now it says to you specifically that x is smaller than 0. So not those two solutions, right? And by the way, dropping that x was a huge and terrible error. Don't do that. Okay. It's definitely a solution. If that was a constant like 6, you can divide by 6. There's no problem, because 6 isn't 0. But that x could easily be 0. That's your third solution. It's definitely supposed to be there. So x is equal to negative a half. You have no choices. I would fill them back in here so that you can see your sequence. And there's the other one filled in so you can see your two sequences. Then you can see what a is. It's obviously the first term. And the common difference, you're just going to go negative 1/8 minus a half, which is going to give you 3/8. And then the common ratio for this one is going to be a quarter divided by a negative a half. And that's going to be negative half. Sum to infinity, which is question B, is over here. So you've got your R value, you've got your A value, you fill them all in. And then sum of the first 20 terms, they'd have to specify how many terms, because remember, this is infinitely large. And the formula is going to be, I'm just going to put my brackets in nicely, n over 2, so number of terms, 20 divided by 2. 2 times a plus n minus 1, which is 19, times by d, which is a given formula, right? And then that's it.